Okay, so we were talking about flux. What is magnetic flux? Magnetic flux is the number of field lines that are going through an area. So for instance, if we have this cross section here, it's a rectangular loop, and here is a pole, this is a north pole, it's painted with red, the field lines are going this way in this direction, and in this particular location there are a large number of field lines going through this. If you put it this way, this is the loop, and the normal to the loop is pointed this way. How many are going through the loop? Well, not very many. Very few are going through the loop. And if I put it at an angle, some fraction of them are going through the loop. So things are changing. So the magnetic flux phi is, I have here, number of loops is dependent by the number of loops. N is the number of loops of wire that is plotted here, so it depends on that. So the more loops you have, the larger the flux going through it would be. And there's area, so let's call the area a vector here. It's got a normal, it's a vector, and there's magnetic field, and it's going through that magnetic field lines, if you like, right? So when it is in this angle versus in this angle, it's different. So this is a dot product here, so n be cosine of the angle. So in one of the demos that we used, where I was sliding the ruler on a rectangular loop, I was changing the area. You can also change the cosine theta, which is, you can rotate this. You can change the magnetic field. All three ways you can change flux. And the change in flux, d phi with whatever that we have, change in flux with dA, or the change in flux with the magnetic field, or the change in flux with the cosine of the angle, all of those things can result in an induced electromagnetic field. So the Faraday's law is saying that change in flux phi results in an induced electromotive force E, some voltage, so the current will flow. So here in this example, what we will do is change the angle. And if I'm rotating this continuously, then what will happen, you can see on the meter there, that I'm producing a current which is varying sinusoidally, right? As we rotate it at a constant velocity, the uniform circular motion, I'm changing theta, the angle, continuously as I rotate it, and you can see that the flux is changing sinusoidally, therefore the induced current is changing sinusoidally, and we are producing what is called as alternating current. It's flowing one way and the other way as I move it. So the uniform circular motion results in an alternating current. The stronger the magnetic field is, the larger the current would be. The larger number of wires that you have in the loop, the larger the current flow would be. And faster you move it, the bigger it will be. I'll leave it there. And if you don't move it, the flux is not changing, it's constant. Right now all the field lines are going through this. So the flux is at the maximum, but it's not changing. So if the flux is not changing, there is no current produced. So this is the effect of the dynamo that we saw before. As long as I was rotating it, there was a current flowing and the bulb was shining. So we will quantify this in a much more careful way in the lectures and in the discussions and so on and so forth.